That's interesting. I never thought of that. All right, so I don't have an announcement slide because I was getting everything ready for the exam, so suffice it to say that we're talking about T-beams. But for those of you that just went through the steel exam that are still in here, everybody did well on homework 3 in here. They're like, we don't care, right? You want an apology? No, it wasn't. No, it wasn't. What's that? Now, hold on. All I'll say about that is this. It says right there on the cover sheet that problem 2 was only worth 20 points. Problem 3 was worth 40. No, hold on. Problem 3 was worth 45. So if you know.
Listen, I've barely passed.
Well, then why that I should be the coolest dude in the room right now? All right. I'm going to try and grade over the weekend. I didn't say I was going to grade them tonight. I don't think that'll work out. It probably work in the opposite manner. What? I'm just saying I've got to focus on the exams. I don't have time for all that. So
if it fails, you redo it with something else.
all right. So I know that everybody is winding down from the exam that we just had, but I said this, we are pressing on, so we are continuing our concrete discussions of T-beams. So back to T-beams. Yes, sir. Yes, and actually I'm glad you mentioned that because I do have something to talk about with homework 3 or homework 4 with concrete, but go ahead. Is it moments?
Yeah, I'm completely confused.
All right. Okay, all right. We do need to talk about that, and I might even like jump off to the side a little bit to talk about the moments on homework 4 because there's some things that I think everybody is doing that's a little, I don't say nerve-wracking, but wonky. That's a good one. Now, I'm going to begin my discussion, and I know I'm sort of going off the notes, but I really think this is important in regards to not just the homework, but what we've been doing in here and what we did last semester. I think this is incredibly important. Now, I'm gonna do this really basically. Okay, so I'm gonna look at 2 different beams. Now, this has nothing to do with the specific homework assignment, but I just want to make a point. All right. So I got a beam over here. I got a beam over here. All right. Now, here's what we've got. Okay. Now let's say we have. Let's make up some numbers. Okay. Let's say we have a 40 kip. No. We're going off. We're getting a handle on this conceptually. All right. Let's say we have a 40 kip load at midspan. Okay. Now let's put some dimensions on this. Let's say that this is 10 feet and this is 10 feet. Okay. So help me out with this. What are the reactions over here? 20. Kips and 20 kips, right? Simple, right? Now, what a lot of people are doing on the homework assignment is they're saying, well, that's not 40 kips. Well, it's 40 kips, but it's over 20 feet. So why don't we turn that into, what, 2 kips per foot? And a lot of people are doing that. They're saying 2 kips per foot. And I think probably the logic is that if that distance is 20 feet, that's 2 kips per foot over 40 foot, so we've got 20 kips, right? And a lot of people are thinking, well, that's the same beam, right? Well, my response to that is no. No, it is not. I no. No, in all honesty, it's not statically equivalent. Okay, and here's why. Let's take a look at the beam on the left. Okay, so first thing that we would do is draw a shear diagram, right? So we would say, all right, let's go up 20, no change. Go down 40, so we're at negative 20. Go over and go up. So this is positive 20. This is minus 20. Everybody okay with that? That's the shear diagram. So the area under the curve, that is positive 200. That's minus 200. So the moment diagram looks like this. It goes up, and it goes down, and this is 200. Is everybody okay with that? Okay, now, here's what everybody's, I guess, having an issue with. They're looking at the two beams on the left and right, and they're thinking, well, they're the same. And in terms of the reactions, yeah, they are. But for moments, not even close. Okay, and here's why. Let's look at the shear diagram over here. Okay, so the shear diagram, I go up 20, but now I'm going down like that, right? So this is positive 20, and this is minus 20. So what's the area under this curve? Well, it's 20 times 10, which is 200, divided by 2, that's 100, minus 100. So when I draw the moment diagram, it's different. It looks like that. And it only goes up to 100. So my point that I want to make is that if you take this and turn it into this, you are going to be significantly under-predicting the amount of moment, okay? And incorrectly so, okay? Now, that may not directly answer your question on homework 4, that is, what do you do, okay? And this is what I will say to that, okay? First off, does this make sense, what I've got here? Okay, all right. Can I move on to the next panel to try and give you a little bit of clarity? So here's what we did in class. Okay, in class, we would have a dead load and a live load, and then we took those and we said WU is 1.2 times the dead load plus 1.6 times the live load, and then we took that and said MU is WUL squared over 8. That's what we did in class, right? Now let's be clear, the goal was to determine that, okay? As long as we followed principles of statics and got MU, we were happy, okay? Here's what I propose you could have also done, not only in class, but on the homework as well. Okay, so you can do this. What if you say, all right, I've got a dead load. Let's take that dead load and say the moment due to the dead load is, let's say it's simply supported, so it's WD L squared over 8. And then down here we've got a live, or not a distributed load, but we've got maybe something like some point loads. So take those point loads and however you need to do it, and I am being a little fast and loose with that because you all should be able to determine the bending moment in a beam due to some point loads, because you've got A, you've got the guides that I provided, and B, we did do structural analysis last semester, so you should be able to draw a moment diagram. You should be able to take that and compute some live load moment, and I'll let you all sort of figure out what that is. But why don't you take these two and do this? And just calculate MU that way, okay? Treat each of them separately, okay? Now let's be clear. You could have taken this approach and applied it up here, and it would have worked just fine, okay? I could take the dead load and do moment due to dead load is WL squared over 8, and then moment due to live load is WL squared over 8, and then factor those, and it would have been the same. I would have gotten the same answer, okay? But this is the stuff that, I mean, I've seen a lot of people try and take, like there's 24 kips, two 24 kip load. and they say, well, I've got two 24 kip loads on the beam and it's 30 foot long, so that's 1.6 kips per foot. That is wrong, like so wrong.
Use this right here in figure 9 where it's
Yeah.
over 60 since they're both equal.
Okay. Whoa. All right. Hold on. Nope. Oh, hold on. Let me answer that. Okay. Number one, you said over 60 I. You're calculating deflections. That's not moments. All right.
This is the figure that we need to go on.
Okay. All right. Here's my response to that. Okay. And the short answer is yes. You're more than welcome to. Okay. But we learned this on, I think it was homework 2. Okay. Those figures are fine, and there's nothing wrong with using them, okay? But the thing you have to be aware of is this, okay? Let me go back to this case, okay? Now, let's say, for instance, that over here on the right, this is my dead load, and over here on the left, this is my live load, okay? So these are two different cases of loading. And be clear, I cannot take the live load and turn it into another distributed load because it won't work out, okay? But let me answer it. I think it's more clearly answerable on this. Okay, this one on the right is case 1 or figure 1, right? Which one's this over here? Figure what? Figure 7. Okay, so bear with. Okay, so watch up here. All right, figure 1. Where is maximum moment? At the midspan, right here in the middle, like 10 feet away. Okay, over here, where is maximum moment? Midspan. Okay, so bless you. Let me be clear on this. Okay, I can take WL squared over 8 and PL over 4 and directly add them because they're at the same spot on the beam. Okay, so to answer your question, my question to you would, like, I would respond by asking this. On figure 9, is maximum moment also at midspan? Is it? It's not? Well, you tell me. Problem 1 on the homework has 2 point loads that are symmetrically placed.
It says between the two loads, so it could be the center.
Then yeah, because it's right there. It's in the middle.
So then you could split those. You could split that in your attributed load, and then moment on that, and then do your figure 9 loads, and then add those together.
What is that? Just do the shear moment diagram.
That's what. Okay, really, what I'm getting at is what Mr. Schaffer's saying is that if you are not comfortable with using those formulas, don't use them. We have shear diagrams and we have moment diagrams for a very specific reason. Okay. I like using those formulas because if you understand how they work, they're a lot faster. But the point is, if you don't understand, that's what this is for, okay? So I really want it to be very clear that if you're having a hard time understanding when you can use one formula and not, take this and throw it in the garbage and do this, okay? Does that make sense? This is important. I really want this to be clear because, A, I want the stuff that we learned last semester to be relevant, because it is, and 2, I want you all to be comfortable with this stuff. I mean, let me put it like this. I'll just go ahead and say it. This is a little easier than what we're doing later when we do shear, okay? Because we really need to track the shear across the beam, okay? Yes.
So this is a question for Dr. Since we're designing a slab,
Mm-hmm.
basically all we're really trying to figure out is the temperature and the steel
Yes.
size of the mold.
And let me also say this for problem 3. You're going to get a really thick slab, okay? You're going to get a really thick one. Because with problem 3, the spacing is 20 feet. So I'm going to tell you, beam spacing that would be 20 foot is really wide. Okay, that's really wide for some beam spacing. So I fully expect that you would have a thick slab anyways, regardless of the loading, just because of that. Okay, so that's point 1. But point 2, you have 200 pounds per square foot, or not 200, is it 200 or 150? 150. Okay, that's no joke. I mean, that's library level loadings. That's The problem we did in class was what? Hold on. Let's get serious. Let's get serious. All right. So the problem that we did in class, what was the thickness for that slab? 6 inches. Okay. The problem that we're doing on the homework, you're getting like what, 14, 15-inch thickness? That's reasonable for those dimensions. All right. So don't freak out if you get a really thick slab. It's a really long spacing and it's got a lot of load on it. So that's okay. All right. No, but I know everybody's brains are frazzled with the steel exam we just had, but we do still have stuff to talk about in here. So, and you all have a homework assignment due on Monday. So,
For the cantilever beam,
all right, go ahead.
you want us to actually draw with the tensile members on the top.
It's not necessary, but I'm glad you recognize that. So, did everybody hear what he said? Okay, so it's a cantilevered beam, right? So the top of the beam is seeing what? Tension or compression? Tension. So you take the rebar and you put it on the top of the beam, not the bottom. Right? Yeah. Because if that cantilevered beam is supporting, like a dance floor, then the people up there are going to have a short party, because.
So technically the depth's going from the bottom to the top.
Yes, exactly right. The beam's upside down. Exactly. Yeah, D goes from the bottom up, and then you have your rebar up top. No, the math doesn't change at all. I just want you to recognize that the tensile steel is on the top. That's important, okay? And plus, I'll go ahead and tell you, that is a classic FE exam problem I've ever seen it. They'll show you a cantilever and ask you, what does the reinforcement pattern look like? And they'll have choice A with the rebar on the bottom, choice B with the rebar in the middle, choice C with the rebar up top, and maybe choice D with no rebar at all. And the answer is C, because tension on the top. That is a very classic FE style exam problem if I've ever seen one. So that matters, okay? Now, the answer is C in that scenario because it was right. Well, so did I. You realize I haven't made the exam yet, right? So to heck with the FE exam, you have a celebration in here on Friday. So, yeah, I'm going to remember that. It's his fault. Everybody, right there, it's his fault.
Oh, don't.
All right. Okay, does everybody have any other questions on the homework? I mean, if you haven't started it, it's going to be a long assignment. So, I mean, there's a number of people in here that I know have already started to chip away at it. And I think they'll tell you, if you haven't even started it, it's going to be long. Am I right? So yeah. So, monsters and Red Bulls are wonderful things. I guess that's all I'll say on that one. Okay, signage sheets going around. We really need to start pressing on with T-beams. So let's sort of recap where we left off and where we're headed. So last time we looked at T-beam analysis. All right, everybody. All right. Settle down. All right. So last time we looked at T-beam analysis, and the first problem that we did was a rectangular T-beam. Now, is everybody clear on what I meant by that? The idea is that if you do your analysis, you start off with C equals T, and you compute how much stress block do you need to achieve equilibrium. And then you ask yourself, well, can I fit that stress block in the flange, or will it extend into the depth of the web? And if you can fit it into the flange and you have a rectangular stress block, then it's a rectangular T-beam, and it's no different than what we did before with just regular old rectangle beams, just ASFY D minus A over 2. But if you've got a true T-beam, the moment capacity is a little more complicated, and we're going to find that out today. Okay, so you cannot use ASFY D minus A over 2 on a true T-beam, okay, and we'll see why. So I want to pick it up looking at example 9b. So we were looking at the flexural capacity, the design capacity of the following beam. Now, we went through this. In this problem, we were given the effective flange width, so we didn't need to go through and do all of that. When we went and computed whether or not it was a rectangular T-beam or a true T-beam, we got that it was a true beam. And if I remember correctly, the last thing that we did is we had actually computed A, right? So here is our beam. This blue area sort of gives you an idea of what our stress block really ends up looking like, because the required area in compression is about 178.59 square inches. The flange only provides 120. So we derived a nifty little expression to compute the distance A, which, I mean, it might be worth starring or putting in your notes or something, or putting on a formula sheet, especially for a homework, just so you have that handy. Excuse me. But ultimately, we got an A distance of 8.185. So that should, if you think about it, that should verify our previous calcs. You know, we got an A distance that was 8.185, and that A distance is larger, and this is important, that A distance is larger than H sub F, because H sub F was the flange thickness, and that's only, what, 4 inches? Okay, so the fact that we got an A distance that's larger than 4 inches validates what we did earlier. Okay, that make sense? All right, now, in terms of moment capacity, this is going to be a little interesting, because think about it, we can do this one of two ways. We can either split this up into simple shapes, or we got to compute the centroid of this. I'm going to come up with a way of determining moment capacity without doing the centroid. Okay, but we'll see that as we get into it. Everybody all right with this so far? Okay. Now what I'm going to do right now is this. There we go. This is 9B. Okay. We have A. We have our stress block depth A. And now that we've got that, one of the things that does not change is our computation of phi, our strength reduction factor. So I'm going to go ahead and do that now, just so I've got that out of the way. So remember, to compute phi, or to determine what phi is, we need the strain in the steel, right? And to get the strain in the steel, we need the neutral axis depth. So I'm going to go ahead and do that now. So we'll go ahead and take care of that. Go ahead and compute phi. All right, so let's see. So we need to determine our neutral axis depth, which is just A divided by beta 1, which A is the 8.185 we got earlier. And what is beta 1 for 4 KSI concrete? 0.85. So 0.85, plug and chug, what does that come out to be? 9.63, so, or maybe 9.629. Just go to 3 decimals. Just keep it simple. All right. I like to carry this to a few more decimal places because strain values can get kind of small. All right. Now, how do we compute the strain? There you go. There you go. And that doesn't change from T-beams to singly reinforced rectangular beams. The only time that strain calcs get a little funky is later on when we look at doubly reinforced shapes, because we got to compute the strain not only in the tensile steel, but the strain in the compression steel as well. Okay, so 0.003 times, what's the D distance for this one? There we go. Minus 9.629. .00635. So what does that now? What's the value that we compare it to for phi? No, 5. Yes, yes. So if it... Yeah, okay. That's okay. So let's make sure everybody's clear on that. If you pass .004, then you've met the minimum requirement for ACI. But that does not mean phi is 0.9, okay? The only time that it means that, the only time we can definitively state that phi is 0.9 is if this value is greater than or equal to 0.005, which it is. Okay. In other words, if you have a value, a beam that's in between, you have to compute phi. So you can get a phi value of like 0.87 or something like that. All right. Everybody okay with that? Everybody good? All right. Now, okay, let's look at this nominal moment capacity. Okay, now this is kind of important. When we did nominal moment capacity before, we used a pretty fundamental relationship for moments, right? We said that to compute a moment, just in general, you need two things, right? You need a force and you need a distance, okay? So let's look at our beam, okay? So we have a beam that looks something like this. We have a stress block that looks something like this. And we have some steel down here. I don't remember how many bars it is, but it really doesn't matter. All right, sound good? Okay. Now, when we did our moment capacity, we said that the moment capacity was a force times a moment arm. Now, first off, let's talk about the force. Did it really matter which force that we used before? Why? Well, we didn't assume them to be equal. We found the distance so that they were equal. So, we basically computed our moment based off of this relationship, and it didn't matter which force that we used because they were equal. Now, that was advantageous when we were looking at just a rectangular stress block and steel. We don't have that here. Geometry, that's a little more complicated. So ultimately, we need to account for the moment generated by this, okay? So this is how I'm going to handle that, okay? I'm going to say that the moment generated by this is going to be the sum of the following two things. So bear with me. So bless you. Okay. So let me draw this out and I'll sort of explain what's going on. And then plus the moment from this. Bear with me. I did better now. Okay. So I propose that to determine the moment generated by this stress block, I propose that it is the moment generated by this plus the moment generated by this. Just split it up into simple shapes. Okay? Everybody all right with that? Now, I've done this for a very specific reason. I'm going to call this, remember that term force-couple relationship? That's essentially what we're doing. Okay? So I'm essentially summing moments when I do this. I'm summing them from the steel. So I'm going to say force times distance, force times distance. So I'm going to call this one over here in the middle, I'm going to call this the web couple. And I'm going to call this the flange couple. All right? Is everybody all right with this terminology? Okay. Now, so for each of these couples, I'm going to need a force, and I'm going to need a moment arm. Okay, so let's start off with the forces. Okay, now let me put some dimensions on this. What is this? Let's look at this. What is this dimension right here? No, okay, yeah, it's 14 inches, but I'm talking about symbolically. What is it? BW. Then I'm going to try and derive some equations that I can use for other beams down the line. Now, what is this dimension right here? That's A, right? Everybody okay with this? So I want to look at computing the force inside this part right here. Now, is that compression or tension? Compression, right? So I'm going to call this the compressive force for the web couple. All right? Now help me out. First off, what's the area of this web couple right here? What's the area, or that force right there? I mean, literally, what's the area? There we go. All right. ABW. Now, what is the stress? Remember, a force is a stress times an area. What's the stress? It's concrete and compression. So what's the stress that we've been using? 0.85 FC prime. Okay. Everybody all right with that? So I propose that 0.85 FC prime times A times BW will tell us that force. Okay? Now, let's chug that out. So we have 0.85 times what's FC prime? 4 KSI. What's A? Now, what is BW? What would you say it was? 14 inches. Okay. So what is that? We'll say just to one decimal place. Just keep it simple. 389.6. Sound good? All right. So likewise, we're going to compute a C sub F, a compression force for this flange. All right. Now, let's look at this. First off, what do we call that thickness? HF. And what do we call, now, let's look at this. What do you think that distance is right there? There you go. B minus BW over 2, or 1/2 B minus BW. Everybody all right with that? So I propose that the compressive force in that flange couple is going to be 0.85 FC prime times the thickness, now watch this, times that distance times 2. So I got a 1/2 and a 2. They're going to cancel out. So I propose it's 0.85 FC prime HF B minus BW. Does that make sense? Everybody okay with that? Okay, so let's check that out. Let's see what we get. All right, 0.85 FC prime. Oh, what? Right now to FC prime, I need to 4 KSI. There we go. What's the flange thickness? 4 inches. All right. What was B? 30 minus 14, right? Did I not? I have it there, right? No, it's you can put the HF on the other side. It doesn't really matter. All right. What do we get for this? 217.6. So I have a second on that. There we go. Get everybody back in the swing of things. Okay. Now, so would you agree? Now, everybody be clear. Everybody follow with me on this. Would you agree that if I add these, that is the compressive force in the beam, right? That's C. So let's just. This is what we're doing down here. This is just a check. This has, no, we don't have to do this, but I'm doing this just to check. So CW plus CF, what is that if I add them up? Well, that's what we're going to check. That's exactly, but I'm talking about just literally add these numbers and tell me what you get. 607.2. See that? I literally, like here, I mean, I'm adding 389.6 plus 217.6. Did everybody get that? Now, let's also check tension. Now, how do I compute the tension force in the beam? ASFY. And what is AS? 10.12. So we'll say ASFY 10.12 times 60 KSI, right? What does that come out to be? So this is a check to see if whether or not what we're doing is right. What's that? Yes, we are. There it is, yep. All right, now, in all seriousness, does that make sense? Because that's important. You need to be able to do that to be able to recognize that, you know, down the line that you're doing calcs where C equals T. Everybody okay with that? Any questions? All right. Now, those are forces. To compute a moment, I need a force times a moment arm, right? So let's do that. Let's do that over here. Okay, so moment arms. And I'm just going to derive them for this. Okay? Now, because when I'm summing moments, these are going to be my forces. My moment arms have to go from the steel to the concrete. So my question is, let's look at the web couple. All right? Let's just look at the web couple. How far is it from the center of the steel to the center of the compressive stress? Keep in mind that this distance right here, from here to here, we have a name for that distance, and we call it what? D. So what is the moment arm for the web couple? D minus half of A. Does that make sense? Okay, now keep in mind that distance is also reflected over here. This distance is also D. So what is then the moment arm for the flange couple? There you go, exactly. D minus H sub F over 2. Does that make sense? Everybody all right with that? So I propose the following, okay? First off, does everybody have everything here, or do I need to move on to another panel? You got this? Okay. I propose that once I can write this out, that therefore Mn is calculated for a true T-beam as follows. CW D minus A over 2 plus CF D minus HF over 2. That make sense? Force times moment arm plus force times moment arm. Literally sum of moments, okay? All I'm doing, all right? What makes it an ultimate capacity is the fact that I'm using literally, maximum stresses. I'm using Fy for the steel, 0.85 Fc prime for the concrete. That's what makes it an ultimate capacity. But the actual mechanics of it is just force times distance. So plug and chug. So I've got C sub W, which is what? 389.6. D is what? 30 minus A over 2, which is, what's A? Plus C sub F, which is? And then it's 30 minus 4 over 2. Is that right? 4 over 2. So what does MN come out to be if you do that calc? First, while some of you are crunching numbers in your calculator, what are the units? Inch kips. We still have kips, we still have inches, so cognizant of that. 16,186.4. Do I have a second on that?
Yeah, for inch kips.
Okay, so I heard a second. So what would that number be in foot kips? Now, is that the final answer? There you go. And what is phi? 0.9. That's why we did it earlier. Went ahead and did that. So therefore, phi mn is 0.9 times 1348. Better than that. Phi mn is what? 1214? Huh?
1213.97715.
All right. Rounded to the tenths place. Is that an acceptable answer? All right. You're not happy about it? I'm sorry.
This could cause a fail and kill a lot of people.
This is where Grandma died.
If that's the answer that you give in court, well, I didn't like the way Dr. Michelson rounded stuff. So. Okay. In all seriousness, does anybody have any questions about this? Like, this is important. I really want this to be clear because I think that this can only serve to further enhance your understanding of what you're doing, not only on homework 4, but on the celebration next week. Everybody all right with this? Okay, let me show you at least a taste of things to come, and then we will call it. But the idea next is, how do we design a T-beam? Well, first off, the only two things I'll say about design right now are the following. So, number one, design of a T-beam is a lot like the design of a known cross-section. In other words, here's kind of the idea. You can either A, use pre-manufactured forms so you already know what the size is, or you can treat a T-beam design as follows. Design the beam independently, design the slab independently, and then go back to the combination of the beam and the slab and see if you can reduce the amount of rebar, and in many cases you can't. So by and large, for the most part, you're going to know what the T-beam looks like, okay? So the main task is to determine the amount of reinforcement necessary. And the way that we do that is we have to make a distinguishing we have to distinguish between whether or not we are designing a rectangular T-beam or a T-beam. Now, just to close it, if you are designing a rectangular T-beam, then the design is no different than what we did before, because it is, again, a group of steel and a rectangular stress block. However, if you are designing a true T-beam, it gets a little more complicated, okay? If it's what we end up doing for our design procedure is we start off simple. We start off assuming that the beam is rectangular. And if that works, we'll just calculate rho required, and that's it. Okay? And then, that's it. Calculating rho required will then take that, back calculate the depth of our stress block to see whether or not our assumption was true. If it is, hey, it's rectangular. If not, what we end up doing is this. We end up going back to this split that we made where we said, okay, we've got a flange couple and a web couple, and we literally treat each of them as if they're an independent beam. We figure out how much steel we need for this, how much steel we need for this, add it up, and then that's the amount of steel that we pick. And that's basically it. It's a longer step-by-step process, but it really requires you to have a good understanding of basics of 0.85 FC prime and ASFY. And if you've got that, you're good. Sound good? We'll go through the specifics of this on Monday. With that, you all have a good weekend. Should I maybe I should move my car after the steel exam? You know.
Will they be graded this weekend?
What's that? No, I drive a Lexus. All right, that's all I got. Y'all have a good weekend.